Ma'am?
Samsia can go ahead.
Okay. In the name of Allah, the most gracious and merciful. In the name of Allah, the most gracious and merciful, it's my immense pleasure to welcome you all to the second day of the International Webinar Series on Emerging Trends in Energy and Healthcare, organized by Department of Chemistry, Annai Hajira Women's College, Melapalayam, Tirunelveli, Tamil Nadu. I would like to welcome our college management, President Engineer S.K. Syed Ahmed, sir, and Secretary Engineer S.K. Kuda Muhammad, sir, and Treasurer Jafar Sadiq, sir, to this international webinar series. I extend my warm welcome to our respected principal, Dr. K. Rajab Fatima, who is always encouraging and supporting to organize this international webinar series. I welcome you, ma'am. On behalf of our management, I welcome today's distinguished speaker, Dr. Vijay Shankar Ashokan from Chalmers University of Technology, Sweden. I welcome you, sir. I welcome the organizing secretary of this 3-day international webinar series, Dr. R. Anuradha, Head, Department of Chemistry. She is the backbone to this webinar series. I welcome you all the organizing committee members of this webinar series. I welcome all the faculty members of Annai Hajira Women's College. I welcome all the participants from across the world. Once again, I welcoming all. Now I would like to introduce the today's speaker, Dr. Vijay Shankar Ashokan. Dr. Vijay Shankar Ashokan has received his PhD from the University of Bergen, Norway. After completion of PhD at Norway, he has moved to Xinjiang University, China, for his postdoctoral research. After the 2 years of completion at China as a postdoctoral researcher, he has moved to Chalmers University of Technology, Sweden, for his second postdoctoral research work. He has published more than 25 research articles in the world-renowned international journals like Nature, American Chemical Society, and Royal Society of Chemistry, etc. He has nearly 355 citations for his research articles across the worldwide. His H index and I-10 index are 9. He has presented his research work at various international conferences held at India, China, USA, Norway, Sweden, Denmark, Sri Lanka, etc. He has 13 years of research experience in electron microscopic field. At present, Dr. Vijay Shankar Ashokan working as an electron microscopic researcher at Energy and Materials Division, Chalmers University of Technology, Sweden. With this introduction, I welcome Dr. Vijay Shankar Ashokan to the second day of the international webinar series on emerging trends in energy and healthcare, organized by Department of Chemistry, Annai Hajira Women's College, Melapalayam, Tirunelveli, Tamil Nadu. I welcome you, sir. Now I welcome our principal for presentations. Please, ma'am.
In the name of Allah, the most gracious and most merciful, I deem it a great privileged honor to welcome Dr. Vijay Shankar Ashokan, microscopy researcher at Energy and Materials Division, Chalmers University of Technology, Sweden, for this webinar. Thank you, sir. Thank you for accepting the invitation. I would like to place on record my gratitude to the management committee members, our president, Engineer S.K. Kuda, Engineer Syed Ahmed Sahib, our secretary, Engineer Kuda Muhammad Sahib, and our treasurer, Janab Jafar Sadiq Sahib, who always extend their constant support and encouragement to us, to all our staff members for conducting all these types of webinars. I would also like to congratulate Dr. Anuradha, head of the department, and other staff of the Department of Chemistry for organizing this webinar. My congratulations are also due to my computer science staff, Mrs. Bhuma and Mrs. Mumtaj Begum, for their technical support extended to me. Thank you. Thank you. Thank you once again, and over to sir.
Thank you. Really, I'm very happy to present a few of my research experience and research results today. Perspective of perovskite solar cell materials. Yeah, I can start my screen.
Yes, sir, you can.
Yeah. So is the screen visible, right?
Yes, sir.
Okay, very good morning again. I'm really thankful to Hannay Ajira College Management and to the Department of Chemistry for such a wonderful arrangement of international conference, including energy and health applications. Even during the pandemic situation of Corona, then it's making a productivity. It's really good to collaborate within such a field of giving exposure and knowledge to the transforming the knowledge to the college students, in particular towards the research workers. So today my talk is about overview of perovskite solar cells. So this is partly work done by our PhD researcher Selvakumar Pichaya. It's mostly a collaborative work. If you see the world map, it's like linking Western Norway University of Applied Science Norway and Chalmers University, where I am working, Sweden, then Coimbatore Institute of Technology, Coimbatore, and Jaffna University from Ilangai. So it's like a international collaborative work, mainly under Indo-Norwegian collaboration project and funding agency Woodforsk. So we are all part of the project. So few of the results we recently published even in Nature Scientific Reports and Royal Society of Chemistry, uh, in particular towards electron layer and whole transport materials of perovskite materials, perovskite solar cell devices. So these are the things we are going to see. Before that, I want to show this slide because this is like our Indian collaboration site from CIT Department of Physics. And also, so here is our PhD student Selva Kumar working in Norwegian University laboratories, and here our team mostly working on different applications like titanium dioxide, the dye-sensitized solar cells, or some health applications research also going on, or with thin film solar cells are going on. So these are the part of work we are carrying out under Indo-Norwegian collaboration work, mainly concentrating like work from Coimbatore Institute of Technology and also part of work carried out in Norway. So with that, I want, before going to the like solar cell, perovskite solar cell devices, I would like to bring few basic details about the photovoltaics. So you want to know what are the photovoltaics. Photovoltaic system converts light energy directly into the electricity. We commonly get the name solar cells. So the simplest form we know or we use every day in our hand is the small calculators, or sometimes nowadays watches are having solar cell materials, and many applications like water heating or like more commercial things from the electricity generation and transforming. It's nowadays it's going to be it's going to replace many electricity or electrical things in day-to-day life in future. In perspective of global warming and controlling the pollution, it's a much needed one in future things. Because of a nearly infinite supply of free energy, like sun gives us 32 into 10 power 24 joules a year, and sun daily provides about 10,000 times more energy to the earth than we consume. So it's good to use such a wonderful or infinite supply of energy in our life to accommodate those things within our need, those things within the technological things what we are daily using in order to make like a sustainable environment. So in that perspective, the photovoltaics is going to be somewhat environmentally needed things without no radiation risk or no noise or no emissions, with long lifetime. That's more important. So if you see here, these are the spectrum of solar radiations starting from such wavelengths covering all the UV visible and near infrared. When we are using all such wavelengths or all such energy, then it's very wonderful things we can do, or we can play with solar cells. So there are many commercially available things like a concentrated photovoltaics or thin film material solar cells or crystalline solar cells. So far, all these things are now accommodated into commercial forms, even though there are more laboratory researches going on with other uh, other recent generation solar cells. but still there are more research works needed in terms of efficiency. So that's why we are now talking about different solar cells, from the traditional silicon towards thin film solar cells with 3 4 semiconductors, then into the recent DSSC or perovskite solar cells, or we can say it's like a multi-junction solar cells, or into the hybrid solar cells, in taking organic or inorganic things into considerations. So there are more researchers needed, and still there are more research works going on outside the commercial world in the research laboratories. So we want to know how these things are working, right? So if you understand the basic energy bands in the semiconductor, including the intrinsic or N-type or P-type semiconductors, so the intrinsic have the energy gap very small, from valence band to conduction band, and N-type with more electrons, and P-type with more holes. So these are the basic fundamentals lying under PN junction diode, or PN junction solar cells, or PN junction energy materials. So if you keep on looking into this, the photons, when enters, it is absorbed and lets electron from valence band get sent up to the conduction band, like shown here, after the incident photon, and few things are go away as like a heat. That's a different story here again. So therefore here the hole is left behind in valence band, creating absorption process. Here the electron hole pairs, it's going on process, depends on the electrical circuit you are connecting. So because of this, only part of solar spectrum can be converted, because only few energies can be absorbed. Those energies are related to the energy band gap of the particular materials. So you need to find a material to accommodate all the energy gaps, or all the energies to get or converted into electron hole pairs, and make an electricity flow into the devices. So that's a search for new materials and new devices, just to make accommodate all photonic energies coming or inciding into the solar cell devices. So these are the basic schematic diagram of P-type solar cells with P-type silicon and N-type silicon with junction, which is connected through the electrical load. When the electron jumps into the conduction band, after this circuit is connected, or the load is connected, the electron moves towards the n-doped semiconductor. Then the hole is moving in opposite direction. At some point, this flow makes an electricity charge movement. So with that, the photovoltaic energy relies on light. So the light is a stream of photons which carries energy. On a clear day, 4.4 into 10 power 17 photons hit 1 square meter of Earth surface every second. So we have to calculate all the energies. It makes the importance to understand how much things we have to use within the solar cell material to accommodate all these photons. So if you see here, however, only photons with energy in excess of band gap can be converted into electricity by solar cells. So that's a more thing, like a fundamental thing we need to understand from all the basic slides which I've shown. Only photons with energy in excess of band gap can be converted into electricity by solar cells. So the solar cell materials, what we are, or the absorption layer, what we are making should accommodate these phenomena, are fundamental, that excess of band gap when considering the photon energy. So when we talk about the solar cell devices, we need to understand these basic calculations, or basic electrical knowledge, like what is short circuit and what is open circuit. So if you see here, with when there is no voltage, if you're connecting the device, the maximum flow current is a short circuit current.
Sorry, excuse me. Can you hold your mic a little bit higher? The voice is low at times.
Oh yeah, okay. Yeah. Now is it okay now?
It's okay now. Thank you.
Yeah, okay. So the short circuit current is due to the generation and collection of light generated carriers. For an ideal solar cell at most moderate resistive loss mechanism, the short circuit current and the light generated current are identical. Therefore, the short circuit current is the largest current which may be drawn from the solar cell. So this is the largest one which is can be drawn from any devices, like particularly in solar cells, what we are talking about now. So the open circuit voltage, that's a VOC, is a maximum voltage available from the solar cell, and this occurs at zero current. So the open circuit voltage corresponds to the amount of forward bias on the solar cell due to the bias of solar cell junction with the light generated current. So when we are calculating this and making a maximum power point, that's a MPP calculation from the graph what we are making with all these calculations. So these things are going to be like a fundamental calculation needed for further calculating a fill factor or the efficiency of solar cells. That's why I want to introduce these things before entering into perovskites, because we are now going to talk about all these things when we are showing the results. So we need to understand what are the things behind what the reference point behind what we are talking. So there are more calculations. Even you can calculate like output current or the open circuit and the voltage. Everything can be calculated with no power is generated on the short and open circuit. The power maximum can be like calculated by fill factor, voltage, open circuit, and short circuit current. So with all these calculations, you can make your own calculation for any devices later on. So there are different generations of solar cells. For example, there are first generation photovoltaics consist of a large area, single layer PN junction diode, which is capable of generating usable electrical energy from light sources with wavelengths of sunlight. These cells are typically made up of silicon wafer. That's a traditional PN junction or traditional solar cells, which was still under like a commercial era. There are more usage or more usage in the industrial world, getting into the applications than all these recent generation solar cells what we are talking. Of course it takes more time, but at least so far most of the commercial solar cell devices consist of such a traditional silicon things. So coming back to our point, if you again take the energy band calculations, like only photons with sufficient energy can excite electron across the band gap, e.g. that's what we are keep on repeating. So only those energy which can excite electron from here to here, it will be usable, and like insufficiently energetic photons with, let's say, E photonic energy less than Eg will not contribute to the photocurrent generation. So the photons with, that is the E photon, and that's the energy of photon greater than Eg, will initially generate energetic excited charge carriers. Any charge in excess of Eg will be wasted heating up the solar cell through thermalization process. So these are the process like unnecessary heating up will waste total energy. So the efficiency will be finally affected in that sense. And apart from that, within the homojunction solar cells, the maximum, like an upper limit, is about 33% of efficiency. It's because of the thermalization, that's a waste of heat energy through the heating process, and there are some transmission energy loss and recombinations, like an electron hole pair can be recombined. So we need to make a junction or the devices in order to avoid such recombination. That's another factor we need to consider when we are constructing solar cell devices in our laboratory even, or the research considerations. So the remaining maximum efficiency is like 33%. That's the possible like an efficiency factor by using homojunction 33 the homojunction solar cells. So that's why we are getting, they do not rely on traditional PN junction to separate photo-generated charge carriers. Here we are using copper zinc tin sulfide solar cells, and the derivatives like using selenium or using sulfur selenium combinations, like it's making more chalcogenides variations, or using dye sensorized solar cells, an organic solar cell and perovskite solar cells, quantum dot solar cells, all lies under the third generation. So far we were talking about PN junction. That's a traditional way of making, getting the photo generations. But after this one, like after second generation, the third generation and fourth generation, it's not lying particularly towards that. So the key point again is to generate and to make a electron and hole pair movement. So we need to make a material in such a way that it can produce electron flow in one direction and hole flow in another direction. So we don't need to particularly mind about doping or like in making a P-type and N-type junctions. Of course, there are even fourth generation, which is like a composite photovoltaic technology with the use of polymers with nanoparticles can be mixed together to make a single multi-spectrum layer. Because so far, the multi-junction solar cell, what we are talking, it's getting different wavelengths or different energy of incident photons through different materials band gap. So fourth generation, it's making a single material, which is like maybe polymers mixed with nanoparticles or other different materials, but it also making like single multi-spectrum layer to accommodate all type of energy, like incident energies. So these thin multispectrum layers can be stacked to make multispectrum solar cells more efficient and cheaper based on polymer solar cell and multi-junction technology nowadays used by NASA on Mars missions. So we are now particularly talking about third generation solar cells. I want to take more notes on this. Like third generation solar cells are being made from a variety of new materials besides silicon, including nanotubes or silicon wires or solar inks using conventional printing press technologies or organic dyes and conductive plastics. So these third generation photovoltaics are designed to combine the advantages of both the first and second generation devices. So based on the technology of second generation cells, but they have slightly improved efficiencies. So efficiency of third generation solar cells then vary between 30 to 60%, potentially able to overcome Shockley Quasar limit of 31 to 41 percentage of power efficiency. So Shockley Quasar limit is imposed by the recombinations and all those things, or those calculations made theoretically towards the solar cell efficiency, considering all the limitation factors, including the radioactive recombinations. So which makes like which makes the solar cell device which lies between 31 to 41 percentage of power efficiency. So these third generation solar cells are potentially able to overcome those limitations. So utilization of materials or cell structures incorporating several band gaps makes solar energy more efficient over a wider band of solar energy, including the infrared energies or wavelengths. So reducing losses due to thermalization. Then there are hot carrier solar cells possible with third generation solar cells. So in particular, when we are talking about third generation solar cells, it's about multi-junction. We need to be more particular about, as there are more multi-junction solar cell devices are made using those third generation solar cell materials. So here, if you're considering like a band gap of 0.75 electron volt, then all those energy, like the photon energy which exceeds this band gap can be utilized. That's what we are keep on seeing, right? So these things are possible here, but when we have band gap of materials band gap of around 2.5 electron volt, then only those energy exceeding this can be utilized. So in a multi-junction, we can combine these different band gap materials, so we can utilize all such incident energies. So when we have such a low band gap, so it's like a high current but low voltage, because these are the things which used for mostly like an highest current value when we are replacing all such energy incident energies, right? So when we have multi-junction solar cells, like we have can be combined with different cells or can be combined with different materials. So each material can use different energies because of the different band gap. So for example, if you see here, it have multiple materials with gallium, indium phosphide, or gallium, indium arsenide, or germanium. So it lies zero point 0.7 electron volt and 1.4 and 1.9. It combined everything, and even like efficiency record was at the time in 2005 when such multi-junction was established. It was like a record of 39 percentage efficiency. So even there can be a multi-junction or multi-band solar cells which utilize different which have different energy bands. So it lists all the incident energies with different in a different scales. So there given possibility for constructing such different complex windows with different N and P type things with tunnel junctions. So these sometimes when you're keep on going on with the multi-junction, in order to increase the efficiency, you need to increase the complexity on in making such considering factors. But that's why we are now entering into another phenomena, for example, within the perovskite. But we have some advantages over the multi-junctions parameters or multi-junction solar cell parameters. So we have to transfer those advantages from multi-junction or the third generation towards a perovskite materials. So here, these are the important things we need to understand about how these three generations are vary with all the efficiency limitations. In that perspective, multi-junction solar cells are capable of high power conversion efficiency, that's a PC, power conversion efficiency, increasing the threshold beyond the thermodynamic maximum set by the Shockley Queisser limit, which makes the efficiency limit between 30 to 40%. That's for the single junction. By having a multiple band gaps in a single cell, it prevents the loss of photons above or below the band gap energy of a single junction solar cells. So in a tandem, that's a double junction solar cell, the recorded efficiency was 31.1%, which is increased up to 37.9% for a triple junction and increased up to 38.8% for quadruple junction solar cells. However, for the metal organic chemical vapor deposition process needed to synthesize a lattice matched and crystalline solar cells with more than one junction is very expensive, because when you are making a multi-junction solar cells, or when we are making a different materials with different lattice parameters, so there may be a lattice mismatch from one material to one material deposition perspective. So it makes again losses of energy in many perspectives, including the defects or including the interfaces issues. So again, the efficiency can be reduced even with the multi-junction solar cells. So however, there are different efficiency calculation which put into a single graph by National Renewable Energy Laboratory. So it tried to cover all the materials, including a single junction or the crystalline silicon cells or thin film technologies or multi-junction cells and emerging photovoltaics, including dye-sensitized cells, perovskite cells, organic cells or organic tandem cells or inorganic cells like then quantum dots. So it utilizes everything. So it shows everything from the 1975 to at least up to 2015. So there are a wide variety of choices of materials, and the efficiency can be seen here with, for example, with perovskites. What we are going to see, it have sudden boom of boom within the PV technologies or the search for solar cell materials. So it started around 2012, and within a few years, it shows an marvelous increase in efficiency or more or less trend towards efficiency calculations. So that's why it's also more important for our consideration towards the solar cell devices. So a perovskite solar cell is a type of solar cell which includes a perovskite structured compound, most commonly a hybrid organic, inorganic lead or tin halide based material as the light harvesting active layer. So the perovskite materials such as methyl ammonium lead halides and all inorganic cesium lead halide are cheap to produce and simple to manufacture. So it have a crystal arrangement like this with A, B. A is an organic cation, which is methyl ammonium, or sometimes formamidinium. And then B is like a big inorganic cation, usually lead. Then X3 is like which is placed here is a slightly smaller halogen anion, usually chloride or iodide. So the perovskites were first successfully used in solid state solar cells in 2012. The perovskite semiconductors offer an option that has the potential to rival the efficiency of multi-junction solar cells, but can be synthesized under more common conditions at greatly reduced cost, revealing that double, triple, and quadruple junction solar cells mentioned above are all perovskite tandem cells with a maximum power conversion efficiency. It's around 31.9 percentage, all perovskite triple junction reaching about 33.1, and perovskite silicon triple junction cell reaching an efficiency of 35.3 percentage. So these multi-junction perovskite solar cells, in addition to being available for cost-effective synthesis, also maintain high PCE under varying weather extremes, making them utilizable worldwide. And most of the perovskite devices can be constructed by using the precursor deposition, making a film, then anti-solvent dispersion and making an intermediate film, then making total perovskite film by heating. So there are possibility for using spin coating or the spray pyrolysis, and mostly it can be constructed in a laboratory. But when we are considering about the perovskite solar cell devices construction, the key point considering is like an vacuum environment in order to avoid the reaction of oxygen or making a deterioration into the perovskite structures. So that's why our research is more important in some perspective. We are trying to make a vacuum-free laboratory model, which we will see in few slides later on. Anyway, so we want to know more on perovskites before going into that. So this is like a graph shows a comparison of open circuit voltage to the band gap for a range of technologies that compete against perovskites. So this graph demonstrates how much of photons energy is lost in the conversion process from light to electricity. In that sense, the perovskite it's also plays a role here compared to other materials in terms of utilization of photons. So this is another graph showing the importance of perovskite's efficiency, pointing out the range of increase in efficiency within few years, because this is a graph which shows the recent DSSC and organic solar cells, quantum dots, CZTS materials around 2010 to 2020. This is like a recent graph. So this is more important in terms of understanding the importance of perovskites materials. So it can be a thin film perovskite solar cell like shown here, or a perovskite on silicon tandem solar cells. So either way you can construct, or you can make an different interface layers. So there are wide options for like wide options in research towards perovskites on different layers, including electron transport or the hole transport, or making the interface between the electron and perovskite, electron transport and perovskites, on hole transport and perovskite layers. So we are mostly working on such interface layers So we have achieved few interesting results using such research. Before that, so these are the typical construction of perovskite solar cell devices, which have conventional NIP, then inverted PIN constructions, or with the mesoporous scaffolds. Within the even mesoporous scaffolds, there are mostly titanium dioxides are used. Sometimes the nanowires are used. So in particular, mesoporous titanium dioxide, that's a mesoporous MP titanium dioxide, is commonly used as a mesoporous layer of MP PSCs, that's a perovskite solar cells, providing a scaffold to support infiltration of perovskite absorber and selectively extract electrons from it. So that's why it's more important, because it extracts electrons and absorbs the energies more predominantly. It makes more like a predominant way to enhance the conversion efficiency of PSCs. In addition, towards the mesoporous titanium dioxide exhibits an appropriate band alignment with the perovskite layer and a long electron lifetime, which effectively reduces the hysteresis behavior of PSCs. So one of the important parameter is long electron lifetime. It has to achieve like a charge carrying mobility in a higher rate. That's why we need some material to be incorporated within the perovskite structure to get such things. So these MP PSCs are generally integrated with compact electron transport layer, that's ETL, which effectively transport the electrons generated from perovskite layer to the external circuit, and also acts as a barrier blocking layer, preventing the photo-generated holes from reaching the opposite electrodes. So these things prevent the holes to reach the electrodes, and hole transport layer prevents electron. It's constructed in a way to prevent electron to be go in these directions. So the compact ETL is also capable of reducing the hysteresis effect in the devices by reducing the defect concentration at the interface between perovskite layer and the fluorine doped tin oxide. That's a transparent conductive oxide layer. Yeah, these are the materials within the perovskite devices. It started from using PbI3 and sometimes there are incorporation of ammonium, that's NH3, within the perovskite material, or changing the ratio of iodide and chloride. Then there are changing, instead of methylammonium, there are formamide can be used, and instead of iodide, the boride can be used. So with each of these different arrangements, the efficiency also kept on increased from 3.8 towards 21.6% in 2017. So there are that's why it's more like it's useful in such a way that you can play with different materials or different combinations, starting from the basic methyl ammonium structures, lead iodide structures, towards bromide and formamide structures. Given here, you can play with different electron transport materials like titanium dioxide or zinc oxide or tin oxide. And then the perovskites, as shown here, you can vary different combinations or the chemical ratios. Then there are possibility for making a different small molecule HTL and polymer HTL or inorganic electrode HTL, because when we are considering the whole organic spiro or other type of OMED, TAD, organic materials as a HTL, it gives some improved efficiency, but also it is very costlier to procure, and it's not always easy to make incorporate it into the interface layers. So there are options for changing different materials in perspective of HTL. That's more important for the recent or the next era perovskite material constructions. Even there are copper iodide can be used, or copper cyanide can be used in inorganic perspective HTL layers. So there are wide variety of choices. That's what I was keep on telling. We were playing with electron transport layer and also whole transport layer materials in our research work. So when we compare the perovskite solar cell performance with silicon solar cells, silicon solar cell is an expensive to purify, but mass production reduced cost significantly. But perovskite solar cells, it's mainly solution processed, lowering the manufacturing cost in an overall perspective. In an efficiency way, there are more single crystal silicon cells achieved with 26.6, but within few years, this perovskite solar cell reached 23.7 percentage. With considering the durability factor, silicon solar cell lost up to 25 years in outdoor conditions. But only problem with perovskite solar cell is the longest reported so far is a stability around 1 year. That's the only thing we need to consider now. Irrespective of other factors, other advantages of perovskite, these things need to be concentrated further over the research things to improve the stability. Of course, there are, in addition to those things, there are many degradation factors like the perovskite lattice and surfaces that's intrinsic, which can be replaced or which can be rectified by using different chemical combinations or different material combinations. There are device interface structures need to be considered. That's more important here. For example, it's shown in terms of air and water degrading the whole transport layer, then it makes more like an more degraded point, which makes rust formation and corrosion of perovskite layer even when it comes from whole transport degradation towards perovskite as it is nearby device structures. So that can be replaced with either some two-dimensional material layer or with nano carbon composites or with nano like combined materials here. So it can avoid reaction with air and it can avoid reaction with water. So those things can be need to be considered when we are talking about perovskite solar cells. So there are many things developed, including the perovskite material layer, which even I showed previously, by using lead-based or tin-based or germanium-based or antimony or bismuth-based combinations of perovskite structure to avoid such degradation and making a lifetime improvement and good stability. And more important is towards making a low toxicity. So we need to find an option towards changing lead based perovskite material. We need to put on thing like considering factors towards such environmental friendly things when we are making a new perovskite materials in future or based device solar cell devices in future. So with all these considerations, I would like to share our experience on perovskite materials. So first we consider the performance of perovskite and nanoparticles based solar cell devices. We synthesized methyl ammonium iodide by such reactions. Even we published it in Material Research Bulletin in 2018. We have made a 4 simple process like ice bath treatment, centrifugation, solvent washing, and dry processes, and make first methyl ammonium iodide powder. Then we use such things with lead iodide with different molar combinations by using a solid state reactions with different ratios, then heat treatment, grinding, which makes different structural synthesis of different perovskite nanoparticles synthesized with different structures. We have even shown with SEM and TM how those structures are varied when we are changing the ratio of lead iodide with methyl ammonium iodide. So here we increase iodide concentrations. That's more important here to be remember. With those different structures, of course, we have used different whole transport layers with our materials. For example, we have used copper iodide or copper iodide and chromium platinum coated FTO, or here copper iodide chromium with our powdered perovskites with different molar ratios, 1, 2, 3 types or 4 types of different molar ratios of methyl ammonium iodide and lead iodide, and try to measure the power efficiency. We have achieved at least very good in terms of like efficiency, at least we can say, within the iodide combinations research. Of course, we reached up to 6.45% at the time, but we try to increase from different scalar parameter. We try to play around those like combinations. We finally achieved a few acceptable efficiency limitations. Then even we have calculated such efficiency with respect to the time, because the degradation of perovskite materials with respect to time is more important to be considered. Of course, there are some loss of efficiency when it keep on going on with different days. We at least calculated those things up to 15 days. Initially, we need to work more on those perspective, considering the stability parameters in future. Then we try to make a nickel sulfide carbon composite whole transport layer. So far, we were talking about a perovskite layer here with different iodide combinations, but now we are now also working on whole transporting materials by using nickel sulfide and carbon composites to reduce the cost by using organic whole transport materials. So we have used different chemical reactions. First, we prepared nickel sulfide, then we made nickel sulfur carbon composites. In detail, you can see this in materials letter published in 2018. This is the reference for the particular article I'm talking about. So we have even checked with all the XRD and all UV visible and all the, even we used BET to understand the surface area parameters. Then we calculated band gap of such materials using topoplats by taking UV visible spectra. And here are the nickel sulfide and carbon composites with different like a percentage of carbon within the composite, like 10, 20, and 30%. So this is the different combined materials we put on into the device structures, and then calculated the efficiencies. Here, if you keep on see nickel sulfur compared to nickel sulfide and carbon, the efficiency is increased, then efficiency keep on increasing, then the efficiency is decreased at some point when we keep on adding carbon, because when we have carbon carbon within the composite materials, there are many surface pores which can effectively used for charge carrier mobility. At some point, when you keep on increasing the percentage of carbon, so it makes a blockage over the whole transport layer. So the possibility for charge carriers to move, it's getting decreased or reduced, in the sense we can say. So that's the factor we need to consider when we are making such composite. We need to know what percentage up to which percentage you can use to get a good efficiency of performance. So that's why we added different carbon percentages and calculated even the degradation point of with number of days. Then we were even recently published, just 2 months back, we published in Nature Scientific Reports this perovskite solar cell, a porous graphitic carbon-based whole transporter and counter electrode material extracted from invasive plant species. Because for making a graphitic and a graphene-based or carbon-based a whole transport material, so it's again the processing and cost factors to be considered. So we want to reduce the cost by using by getting carbon from naturally available or bio-based synthesis. So this because this carbon-based material need to be used here, because of these advantages, it is hydrophobic in nature. If you remember from the degradation slide, those reactions for water or moisture into the whole transport layer makes a corrosion even up to the perovskite layer. So that's we need to consider the hydrophobic nature of material to be introduced with whole transport layer. This can be low temperature solution processable, easy and flexible fabrication, and low cost at larger scale, or similar work function considered to other HTL material, same optical property to polymers and fast charge transfers. So you can do many optimizations when we are synthesizing. Of course, when we tried with these things, we tried to get like a bio extraction of porous graphitic carbon. We named it as ECGC. That's because get from the Ecornia crassipes. We prepared biochar in the first process, then extraction of porous graphitic carbon from the prepared biochars. So it's like a two-step process, which shown here, and you can see this in detail in scientific reports which published in 2020. Then from the first point, we are now moving to the second step. Here we use the extraction of graphitic carbon paste from the biochar materials. Here we used biochar precursor material that's subjected to two-step process with an acid pre-treatment followed by heat treatment. So we make a carbonization process here, try to graphitize those things by the parameters we given here. Even those things were clearly noted in our paper, so you can see that we have used different annealing temperatures, 450, 850, and 1000, to understand the graphitization process and the influence of such different graphitized material into the efficiency parameters. And the third step is preparation of carbon-based HTMs. So here the different annealed samples were taken and mixed with alpha terpenol and chlorobenzene and were sonicated for 1 hour and obtained final graphitic carbon colloidal paste, which is used for PSC constructions. We used facile brush painting methods, so just like how you paint paint the wall by using a brush. The advantages of such method is like high-speed fabrication, a low material loss, a processability on various substrates, even on non-flat surface such as fence and roof. Moreover, because direct brush painting of limited solution on thermally controlled substrate causes a fast solidification of flame, a critical control of flame thickness. You can get smoother surface morphology if you are keep on getting experience over such brush painting approach. So these are the our sample by using brush painting approach. These are the carbon HTMs prepared with different annealing, 450, 850, and 1000 degrees centigrade. So we have even first started with analyzing such GC which is annealed with 450, 850, and 1000. We try to find the graphitization parameters by using XRD and Raman. So the ID-IG ratio, which shows 0.75, which is directly represented like these things. That's a graphitized annealing temperature, 1000 degree produced more or less comparatively higher graphitized material when compared to 450 annealing temperature. That can also be visualized by seeing the graph of XRD peaks, which shows a very intense peak of 002 at around 22 to 24, which is towards more graphitized region. So we have successfully constructed or we successfully synthesized graphitized carbon with different annealing temperature. That's what we want to say here. We also used BET analysis and calculated the different pore parameters and the surface area parameters. And if you see with 1000 degree annealing temperature, the surface area is enhanced with 1000 square meter per gram, with pore size reduced to narrow slit like pores like 19.9 nanometer. That's successful of this annealing temperature. So this is a basic perovskite material we synthesized. We used this perovskite material and combined with HTM material, which we make using graphitic carbon materials. Here from the TM image, you can see about how the graphitic carbon is layered around such perovskites. Because here we have used, if we have not only used HTM, like a carbon-based HTM, we also used interface layer by using a perovskite and graphitic carbon material. That's why we just combined with these things. In addition to the basic perovskite material we have already in the device, we will show you, for example, here. So this is a gold electrode. Then the breast painted carbonaceous layer. This layer is also made together with perovskite material. Then the perovskite layer was formed here, and the porous titanium dioxide, which is needed for electrons and transport layer. Here is the dense titanium dioxide and FTO glass plate. This is how we constructed our device. We have shown different primary characterization parameter of these devices with different annealing. We try to calculate the efficiencies, and we have constructed number of devices by using different combinations. For example, you see here with the perovskite layer and 1000-degree annealed carbon mixed with perovskite, because this is going to be the interface, and with different ratios we have used, and different morphological carbons we have used. We have constructed a device. So we have constructed number of devices, sorry. It's shown here with different combinations of HTL, and we have calculated the efficiencies. Then finally, this layout is showing only the combinations of different annealing temperature to show how those annealing temperature influence the efficiencies. For example, here. So with 1000-degree annealing temperature, we have improved 8.53 efficiencies compared to other annealing temperature and other carbon and carbon nickel sulfide, which we shown in our previous report. So this is one of our like a recent research. Then we have also now concentrating on electron transport layer by using zinc oxide combined with titanium dioxide. For getting zinc oxide, we have used
excuse me, sir.
Yeah.
Sorry for the interlude. The voice is breaking in between. It's getting low.
I don't know. It should be okay. Okay. Is it okay now?
Sometimes it is not audible, sir.
Oh, sorry for that. I'm not sure why it is. Yeah. Hopefully it's okay now. I try to make as close as possible.
Not because of that. I think the connection, mic connection is not good.
Oh, okay. Okay. I try to reconnect now. Is it okay now?
Okay, sir. Thank you, sir. Okay.
I'm not sure. Sorry for that. Okay. So we have used a green synthesis of making a zinc oxide nanoparticles from such a leaf, and we get such a process, and it's published in New Journal of Chemistry, Royal Society of Chemistry journal, which we published very recently. So you can see how we synthesize such zinc oxide in this paper. So we have used XRD and UV analysis to show how these zinc oxide nanoparticles were synthesized. And we have used like a deposition of perovskite layer by our routine way, which we already used in other research, which even shown here how such things are made. Then here, this more important thing about such zinc oxide nanostructure into the titanium dioxide electron transport layer is because of the micro-sized pinhole, which now reduced to nano-sized pinhole. That's more important to combine such titanium dioxide and zinc oxide things. For example, it's because of it has to avoid the recombinations. When we have micro-sized pinhole, there are possibility for electron and hole interactions as shown here. But when we have the green synthesized zinc oxide nanostructures combined with this compact titanium dioxide, such a recombination can be inhibited. That's important of to understand such micro-sized pinhole and nano-sized pinhole within the electron transport materials. So this is how we constructed by using zinc oxide and nanostructures above the compact titanium dioxide. Like it's over the interface between perovskite and titanium dioxide. Here we have used a traditional whole transport layer. Of course, we have used different whole transport layer, but at least within this paper, the report shown here is using spiral transport layers, whole transport layers. So this is the efficiency diagram which we pointed out, and we calculated with compact titanium dioxide, then with zinc oxide nanostructures, then with combining this bilayer, like using a bilayer of combining titanium dioxide and zinc oxide together within the device. So we try to calculate the efficiencies which shown using the bilayer, the efficiency is improved. Such graph is shown here with the IV diagram. So these are the things we have worked so far towards electron transport layer and towards whole transport layer, and also over the perovskite materials. It's a broad research work carried for our for the PhD research student who recently submitted his PhD thesis even. So these are the things we want to show in this talk. Finally, I'm acknowledging Western Norway University of Applied Sciences and Coimbatore Institute of Technology. So we are grateful to TechCube and also the Woodforks program. That's an Indo-Norwegian collaboration project funded this research. And thanks for listening. And I think if you have any questions or like for further collaborations, just try to mail me at vijayashankar.metsi@gmail.com. With this, I'm concluding my talk. Thank you for your kind attention.
Thank you very much, sir. I'm Dr. Anuradha here. It's an instructive and illuminating presentation.
Yeah, thank you for that.
There are a lot of questions we have seen in the YouTube live. Can I ask, sir?
Yeah, we have a few minutes time at least. I try to cover those answers. Otherwise, I will answer through mail even later on. Because I have another talk. I have to go quickly.
Okay, sir.
Yeah. So please read out. If I able to answer, I answer it quickly.
Important question from the tomorrow's speaker, Dr. Kalpana Setu. She has complimented that it is an interesting session. Generally, when solar panels became very hot, their efficiency decreases. How about this phenomenon in third generation solar cells?
No, it's not about third generation solar cells. It's about the materials, I can say. So we need to, that's what I was keep on repeating, the material perspective. You need to consider the materials point when you are constructing a device, as in particular towards multi-junction or perovskite solar cells. So all those parameters can be avoided if you're considering these points.
Okay, so one more question from Seema from Manoramadiam Sundaranarar University. In which way etching of perovskite material will affect solar cell performance? Could it be a prominent way to enhance the performance of PSC?
Yeah, in which way it is etching, is it?
Yes, sir.
Oh, it's because of yeah, of course. I shown some graph or shown some like a model diagram. When we have HTL or ETL, where which can be when it is react with oxygen or moisture, first it reacts with those things. When those layers it's get affected, then perovskite, as it is already an like an oxygen lover, it easily get reacted with that one. That's why the degradation point of perovskites is high when compared to other solar cells. So we need to avoid such all the degradation point in starting from whole transport material etching or from the electron transport or directly towards the perovskites because the perovskite itself is the structure itself is ready for such a reactions. That's why we are considering that point.
Okay, sir. Sir, I have a doubt. This
Yeah.
is since its operational stability and the reproducibility are much lesser for this one. How about the commercialization of this perovskite cells?
No, I think the commercialization, I am not sure how far it has reached now in the commercial world, but the perovskite layer was initially, it was used as a dye in dye sensory solar cell when it was started, like when the research was started to think about perovskite material. So at least in DSSC, it should be used like the commercial thing, but I'm not sure the perovskite is directly started to get into the commercial world because of the degradation point, because the maximum limitation is so far achieved is 1 year, as I shown in my slide. So I'm not sure. We have to check that.
Oh, thank you, sir.
Yeah.
Okay, sir. I'll mail all other questions to you,
Yeah,
sir.
please.
Now
Yeah.
I'll call upon Dr. Ms. Lishavi for vote of thanks.
Good afternoon, everyone. Respected speaker of the day, Dr. Vijay Shankar, Chalmers University Technology, Sweden. Respected principal, Dr. K. Rajab Fatima, our beloved HOD, Dr. Anuradha, my dear colleagues and all the participants, I deem it a great honor to propose the vote of thanks to all who have helped us in making this webinar such a resounding success. First of all, I would like to thank our distinguished speaker, Dr. Vijay Shankar, for making excellent presentation and making this webinar interesting and meaningful. Thank you, sir. We are grateful to our President Haji Engineer S.K. Syed Ahmed, Secretary Haji Engineer S.K. Khuda Muhammad, and Treasurer Haji Jafar Sadiq for their support. I would like to express our profound gratitude to our Principal, Dr. K. Rajab Fatima, for her support and commitment to this webinar. I would also like to thank our HOD for her moral support and guidance. I am happy to express vote of thanks to our technical team, Mrs. Booma and Mrs. Mumtaz, who have made this webinar a grand success. I thank all the people who have participated actively and making the event success. Once again, I thank all for your cordial cooperation. Thank you.
Thank you very much, sir.
Yeah, thank you, madam. Thank you for such wonderful arrangement. Thank you. Bye-bye.
Thank you.
Thank you, sir.
Shall I end it?
Yes, ma'am. Thank you.
Thank you.